Okay, last example for the day. We'll add in a hypothesis test for this example. I do want to do some examples where we pull a large data file and crunch raw data that has more than just 10 numbers in it, but that's what we'll do tomorrow. So we'll do some more examples of estimates for one mean tomorrow. And the difference tomorrow will be that we'll have some examples where we actually get data from a large data file. Okay, so my last example today is just going to be another one where we have the summarized data, but we're performing a hypothesis test this time. So we collect body temperature readings from 106 people. And we have the summary data. So the sample mean was 98.2 degrees Fahrenheit. Okay, I'll just put F there for degrees Fahrenheit. And the sample standard deviation was 0.62. Okay. So we were expecting 98.6 degrees Fahrenheit because that's supposed to be body temperature. Of course, in reality, body temperature goes up and down. If it goes up a lot, you have a fever, but it's not unusual for it to go up a little bit if you've been exercising, or maybe you just had a meal, your body's digesting, that's enough work to raise your body temperature. Sometimes it's lower because you're resting, or you were just outside and it was a cold day or something. So your body temperature actually goes up and down, but we sort of think of 98.6 as being the normal body temperature. So my question is 98.2, is it indicative of there being something special about these 106 people that make their body temperature lower? Like maybe they were all doing some activity that lowered their body temperature. Or is that just within the normal variation of randomness and there's no statistically significant difference? So let's run a hypothesis test at the 5% significance level to check if our group was somehow different than normal. Okay, because if this 0.4 off is a statistically significant difference, then maybe our sample wasn't just a random sample of random people doing random things. Like maybe there was something special about that group. They were all like it was a certain time of day, or there was some activity they were doing that made it so that they had lower body temperature. So I want to check if this is a statistically significant difference. So let's flip over to Minitab, and basically we're going to plug everything in the exact same way we did before, except we're going to check the hypothesis test box. And that's pretty much the only difference. So stat, basic statistics, one sample t. We have the summarized data. This time our sample had 106 people in it. Our mean was 98.2. And our standard deviation was 0.62. 0.62. We want to perform a hypothesis test, and there needs to be a null hypothesis number. Our null hypothesis, the number we're comparing to, is 98.6, which is supposedly the normal number. And our alternative hypothesis, that there's going to be some kind of difference. Now, remember that our default alternative hypothesis is not equals. And this time our sample came out on the low end, but we only knew that after we saw the results of the sample. You know, the scientifically responsible way to run these tests is to have your hypothesis before you collect data. Now, you're not supposed to make your hypothesis match the data because that doesn't indicate that you sort of like that your science has any accuracy to it. And you're supposed to have your hypothesis before you see the results. And so we shouldn't say that we expect the body temperature to be lower because that's what happened in the sample. We should pretend that we don't see the results of the sample because in real life, that's what we would do. We would make our hypothesis first and then collect the body temperatures and see what happens. So not equals is what we should choose here. I'm going to change this confidence level to 95 just because 95 goes with 5% and we're testing at the 5% level. I didn't ask for the confidence interval, but Minitab's going to make it anyway, so we may as well compare and set it the confidence level to the to the companion of the 5% significance level that we were asked for. Okay, so I'm going to hit OK, and let's see what we get. So I have my confidence interval here, and 98.6 is not in that range, right? The normal body temperature is supposed to be 98.6, and my confidence interval for the mean of all the people that I could have tested, excuse me, I have to cough again. 98.6 isn't in this range, so it's looking like we do have a difference between what we did and the null hypothesis. So null hypothesis 98.6, alternative hypothesis something other than 98.6, and there's our p-value. It's small. It's 0 to like 10 decimal places or something like that. So what is that? 8? I think it's the 9th decimal place that finally has a 1 in it. This minus 6.64 basically means that it talks about how far down the bell you were. So we're kind of down the left side of the bell, the low end, by like 6.6 standard deviations down the bell. That's a long way. 95%. Like in order to be within the 5% hypothesis, like significance level, like to get a p-value bigger than 5%, you really can't go more than 2 standard deviations down. Remember that like 1.96 number we use for 95% confidence intervals? That's like here we're going 6 standard deviations instead of 1.96. So yeah, this is way down the bell. So the tail is really tiny over there. So we actually have very strong evidence that the body temperature here is not 98.6. So what does that mean? Well, it probably means that there was something about this group and the way we tested them that was making it so that their body temperature was on the low side. They all or most of them had something in common that was lowering their body temperature from the normal level. All right, so small p-value. We have strong evidence that the null hypothesis is false, and instead the alternative hypothesis is true. All right, I think that's enough for today. We'll do some examples next day where we pull raw data in from a file.